Last time we got a little stuck there on this laser tag tool, trying to fit everything in here with the components. So if I can talk today, the goal is relatively simple. We just need to handle a few different states. We do kind of have this like persistent overarching state of like, are you alive? And we don't really have like a cheap way to persist and access it. We could build one of these, but this little data node is actually much cheaper. It's two yuan cheaper than one of these, and we don't have to implement any logic to store it. We can just write the value here, and then we can read the value off of it, a simple flag. We could put it in memory, but memory is a little bit more limited because we have only two readers, really, that can exist. So we have a data and an address pin. Like this is data, this is address. So the data will actually read the value of a cell, and the address will actually update the pointer to the cell. So we've got two data, two address pins, and they're independent of each other, so we can change this address. The data is not independent. They both write to the same cell. The addresses are independent. They can update the pointer. But if you have two things reading from like A0 and D0, then you don't know which one's going to set A0 first. So you've got to kind of like do some synchronization there. We could put in a layer in front of it, but we're already struggling to fit all of our logic in here. This one is really code light, so the assumption would be like, why not use the smaller one? But then you can see that we've got several things plugged into it. So we've got these pin inputs. So we need at least two pin inputs. This one actually uses an X input, which is like a data input, and that uses a data input. But this one needs to know, I guess reloading technically could be independent. Reloading can happen independently of whether you're alive or not, but it needs to update the ammo data here. And then trigger doesn't. What else needs ammo data? I don't think anything else needs ammo data. We may not even need this, which is why it's kind of floating up here. We don't have anything plugged into it. We could store ammo data here and just determine if we need it based on whether trigger's pulled. Trigger does need to know if you were alive, though, which is yet another pin. And we don't have any more pin inputs here. So that's a problem. That is a problem. I suppose we could do a communication layer transfer. What is it? I'm trying to figure out what this one's doing. So this one's saying, this one's doing the check if they're alive, I think. Well, let's see what it's doing right now. So if pin 0, which is reload, then we move 0 to X0. Don't know why we'd move X0. Move 0 to X0. Okay, that must be an error. Let's re-implement this. All right, so if reload is hit, what we want to do is we want to move, I think it's X2, X3. We want to move X3 into ads running. So I'm going to stop for a moment. X3 into the accumulator, because that's where we'll store ammo for now. Why not? And then we'll pause for the ad. We'll just hope everybody's having a great Tuesday. Alexi said hi. Thanks for popping in, Alexi. Thanks for stopping by. Yeah. I don't really want to talk too much about this. I may just go play. What we got? We got a minute and a half left. Yeah. So anyways, yeah, I hope everybody's having a great Tuesday. as we near the big holidays, at least in the States. I know some other places celebrate as well. So I hope I hope everybody's looking forward to it. At least some rest and relaxation for a couple of days. That'll be good. Similar to Thanksgiving, I'll probably take some time off to be with the family. I don't think that's going to interrupt anybody. Nobody really depends on me to be there every week. So, no worries. But yeah, it'll be, it's easy to kind of come back into this game as well. All of the context is kind of in those emails. So we can easily see like, what are we working on? What are we supposed to be building? That kind of stuff. Ooh, let's see what else. Yeah. I fell behind on my video editing. Yeah, I haven't edited videos in a while. Need to get back on that and try to get the regular releases back on YouTube. I try to stay like 2 weeks ahead of my current output. So like each video I record goes into a queue, and then I release them ideally on my off days except for Friday. Just so, because I only stream 2 days, so I don't want to release 3 videos a week or else I'll run out of videos. So to make sure that I always have videos, I try to do like a Monday, Wednesday VOD release on YouTube. But I've fallen behind on editing, and the ad break should be ending soon, so I'm gonna stop filling the void with chat. Get back to working on this this problem here. So, anyways, yeah, as we were saying. We're going to re-implement this. So this is going to be P0 is our reload pin. So if reload is pressed, then we're going to move the ammo value into accumulator. Otherwise, we're just going to do that. Otherwise, we're going to test equal P1. If that's pressed, then that's the trigger. That means somebody has pulled the trigger, and we need to check to see if the player is alive. Now, we don't have pin input. We don't have pin input to see if the player is alive. So that's what X2 is. X2 is kind of a trigger to this one to do the firing. And so that's what we're going to do. We're going to move, because it doesn't really matter what the value is. We're going to move 0 to X2. That's just going to say, hey, wake up and do a thing because the trigger was pulled. We can actually do the alive check here, but we can also do some more here, right? So I guess what we'll do is we'll put a jump fire in here, and then we can put a fire label here, and this can sleep, well, where do we sleep for 1? We'll sleep for 1 here. That's just gonna jump done. So we'll put a done here. I don't know why that's... We're gonna sleep for 1. We have to sleep, so we don't need that to be gated anymore. We're always gonna run fire. So we move 0 X2, but first we need to make sure if I guess it's greater than 0. If the accumulator is greater than 0, so if the accumulator is greater than 0, then we will fire. We will also sub 1 from the accumulator because we just fired a round. Oh, but does that count? When the player is alive, pulls the trigger, and has ammo remaining, the gun should fire, and the ammo count should be decremented by 1. So I guess what we want to do is we really want to say we'll just test equal X2 is 1, so we'll read from X2. If that is 1, then that means we did fire, so then we sub 1. So we just check to see if we have ammo. If we have ammo, if we don't have ammo, we're going to jump to done. And I think that's going to be good. That's going to be good. So then down here, we'll rewrite this. So I don't know where we were. We're going to sleep X just on X2, just like we did, because we don't need to do anything if we're not. Why can't I wire that up? That needs to go there and there. Okay, so sleep X2. So waking up means we're going to try to fire. So we need to know if P0 is 100. If it's not, then we're going to move 0 on X2. I guess we need to move X2. I don't think I have like a null. Just put it in DAT. I don't need it. Actually, I don't even need accumulator. Let's put it in there. We're going to move 0 to X2. That's going to be false. And then we're going to jump done. Done will be, or we'll jump like loop. Yeah. Okay. I don't know what you're talking about. Didn't ask you anything about music, Siri. 1 second here. I need to mute myself. Talk to my dog. Pup. Hey, pup. Stop that. Yep. She's got a hot spot on her tail that she keeps licking. Gotta tell her to stop every now and then. Yeah, I see you. Yep. All right. So we'll put our loop label at the top. Loop. Okay, we're going to jump loop there. So if it is equal, then we're going to execute the firing. So we're gonna move 1 to X2. So we're gonna get that out of the way, and then we're going to I don't know what you're for. I don't think we need that anymore. I'll just go straight there. That's what it's for. That is what it's for. SLX X0, move X0 to P1. Yep, that's what we want. So then we can move 100 to X3. Okay, let's try and see where we're at. We come in here. We're moving along. We get a respawn hit. We are now marked as alive. We now get a trigger pull. But we have 0 ammo, I believe. So that should jump fire. Yeah, so we don't fire. We get another trigger pull. And we don't fire. We get a reload. Reload comes in. Our ammo is now set to 5. And then we get a fire call. So we test the fire. We move 0 to X2. That reads the value. We check if we're alive. We are alive. We move 1 to X2. So we say we fired. That subtracts 1 from the ammo. And then we move 100 to X3, which moves it out. We fired. Ooh, wait, why is it still going? So this needs to actually sleep 1, move 0 to P1. I think that'll work. Let's get back over there where we were at. We've got the firing, fire. We've reloaded. Everything seems to match up. Let's simulate. Did we do it? Actually, let's reset because we want to get rid of that. We don't need that. I don't think that costs anything, but still. Bridges don't cost anything. Okay. You know what? I do not need this because we have that. Perfection. That just needs to go to P1. And then that sleeps one. Move 0 to P1. That's going to cause an error, probably. I can almost guarantee that's going to cause an error. I could be wrong. There is a case where it does cause an error. We spent a lot of money. We used a lot of power. And we wrote a lot of lines of code. We're a little high on everything. I'm happy with that because this one's pretty tough. There was a lot of things to fit in. And obviously, that's the approach that I saw. I don't know if I could easily clean that up at all. Usefully, Usefully clean that up. All right, anyways. Awesomeplex, yeah, that was the name of the place. If you were not here last time, the place that we were building this laser tag thing for was going to be the Awesomeplex. He's purchased the building for his first. I can't bring myself to write it out as first location. Not sure I want to imagine how much of his retirement he's put into it. It's also nice to have a dream. Yeah, cool dad. Hope you're all sitting down right now because this one is going to be big. How big, you ask? Well, you just might be talking to the guy who negotiated a deal to make all of the light-up, color-changing vapes that Cool Dad is going to give away. Well, not the best thing to give away. I mean, not healthy for folks. I don't know. We really want to do cool stuff for that. Okay, we got color-changing vape pen. Radio RX is a non-blocking X-bus input connected to a radio receiver. Red, green, and blue are simple outputs connected to an ultra-bright RGB tricolor. So we need to pull up the spec to try and figure out what's going on with this RGB thing. Pop open that browser that I will absolutely not forget to close this time. Pinky promise that one. So we're looking for, I'm just kind of scrolling through here pretty quick because they've got pretty pictures. We're looking for something that matches this color thing. If that doesn't work, we'll have to look for like color or something. Yeah, that didn't seem to work. So now we do like a Control F, like color. That's Colorado. That is the only thing in there. Okay, so I don't know what RGB is. Let's look for red. That's reduced, required, ignored, redundant, stored. Okay, maybe blue is less used. Wavelength. Wavelength-based color classification. This may be what we want, but I could be wrong. We'll just have to see. Ultra bright RGB tricolor LED from top to bottom. When a data packet is received over the radio, pulse the LED as specified. Red intensity, green intensity, blue intensity. So I'm going to assume this is red, this is green, this is blue. And then the pulse duration. If a data packet is received while a pulse is in progress, interrupt that pulse. Okay, so we need a pulse. And we need to be able to interrupt the pulse. Red, green, blue. Looks like these values are -999. So we receive that. Pulse duration 999. So I assume that goes on forever. This 1, 2, 3, 4. Oh, that's how long we pulse it for? Or does 999 turn it off? It does not turn it off. Okay. I guess 999 just means like every tick we go down one. Okay. I think we can do this with Well, we've got to store the red, green, and blue intensities. So I think we're going to need 2 minimum of these things. Now, these are they pins? They are pins? Are they X's? That's what I was afraid of. They are pins, and none of these have 3 pin slots on them. This one has 2 pin slots. Yep, 2 pin slots on it. This one, yeah, so the intensity of 25 we couldn't store anywhere. And they took away our flippin' data component. Like, this would be great for our data component. We've got 1 reader, 1 writer. So we write the current values of the pulsing, and then we write the logic of pulsing it. That would be perfect use case for this thing, but it's not recommended for this problem. So, well, isn't that just amazing? So the pulsar needs to write these values out. So we probably just need, I don't even have a thing that can store 3 numbers. This can't even store 3 numbers. It can store 2 numbers, and that's it. So we need 1 of these and 1 of these, and they need to basically be somewhat in sync. And then we need this to send an interrupt signal to both of them. So that. So it may need to be implemented longer. I don't know if longer is the right terminology there. May need more code. Okay, so that needs an X input. So probably just do need 1 of yous. So receive goes into an X input. Let's move you up there. And then you've got a pin input here, which can't go anywhere. Crud. But you can go there. So this pin input, we can get rid of that. Yeah, so this pin input can go red. Oh, I need that pin input. So you need to come down, and you could probably afford to go down here. Whoa. P0. Boom, 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 boom. That's not ideal at all. Because, oh, no, that's fine. You will go there. And I could bring this, oh, I can move this too. Yeah. Totally. Can totally do that. Okay. So I think that's everything wired up. That's probably more expensive than it really needs to be, but red, green, blue. So this is going to be our blue one. So we're going to, I guess we're going to read a value from X to X0. So if it's, we can't copy it to accumulator, so it's going to have to be just a flag. If it's, what are the 2 things we're going to need to do? I mean, I guess we'll write to it every round, so that's fine. So what we'll do is, let's see, when we get a new value, yeah, we have to change immediately on that frame. So we're going to say if SLX, sorry, X0 is 1, then it means we're going to set a new value. So we need to copy X0, which we've already read from, so that's gone into the accumulator. That's our new blue value. And it's not copy, it's move. I promised I wasn't going to leave it open, and what did I do? I left it open. At least I caught it earlier this time. That's better than nothing. Okay, so we're going to move it. If it's one, we're setting a new value. We're going to move it to accumulator. And we are going to but we don't we don't know if we pulse. We don't know if we pulse, right? Because the pulse could end. I guess when a pulse ends, it'll just be 0. So that's fine. So move x0 to accumulator. That might be too complicated for this. Reading, parsing, determining if we should pulse. We'll figure it out. We will figure it out. Moves x0 to the accumulator, so that's our new value. And then we pulse, so we move the accumulator to P1, and we sleep for 1. Yeah. So only if it's 1 do we do anything special. And that's basically going to be like what we do here, except we've got 2 values. So 1 goes into the accumulator, and 1 goes into DAT. And then we're going to move the accumulator to P1, and we're going to move DAT to P0. And then we're going to sleep 1. That could actually probably be a small one. If this works, that could be a small one. So this one is going to be the complicated one. So we are going to copy, we'll move ACC, move X1 into DAT, ACC, and we're going to test equal ACC, I guess really test GT ACC. If it's greater than -999, we've got ourselves a color value. So new jump read. So we'll mark our read here, which is gonna copy. That's red. Red goes x0. So we're gonna move ACC to x0. We're going to move x0, x1, which will now be blue, to x0. And, it's RGB. Yeah, red, green. And then blue is the third value. Are they trying to mix this up? Red, green, and blue, and then red, green, and blue. Yeah, they're in the same order. Move x1 to x3. So that's our green value. And then we move those values, we're good. So we just kind of loop, I guess. And then we jump loop, probably. The other thing that we need to do is we need to, I guess, if it hits 0, so that would be 4. We write 4 in there. Then 3, then 2, then 1, then 0. So if it's 0 when we start, if DAT is equal to 0, we're going to jump 0. Jump 0. If it's not equal to 0, we're going to move 0 to x0, move 0 to x3. And then down here, 0, we're going to move 0. Oh, yeah, we got to move 1 to those things first. Move 1, x0. So I think if I send the communication differently. Let's put in a communicator node. It can probably just be one of these. So this is gonna x0, 1. So if x0 is equal to 1, then we're gonna move 1 to x0. Oh, it needs 3. We need 3. We need two x outputs and 1 x input. Okay, so x0 is 1. If that's equal to 1, then we're gonna move 0. We're gonna move 1 to my mouse always right over where I'm typing. Move 1 to x0. So what we're gonna do is if x0 is 1, so that means we're gonna set a new color. We're just gonna move the colors. We're gonna get all 3 colors here sent directly to us. We're gonna move it, and we can do a couple of different things here. So I guess we don't have to store colors, so we can actually move x0 into the accumulator, and then we'll test if it is equal to 1. So 0 will be just like work. 1 will be set new colors, and 2 will be 0 out. So we'll move 1 to x0 to x3, and then we'll move x0 to x3, move x0 to x3. And then we'll move 1 to x2, and we'll move x0 to x2. And that is all the colors, because we didn't even account for setting the dat value there. Then we test equal. If accumulator is 2, then we move 1 to x3, move 0 to x3, move 0 to x3, move 1 to x2, move 0 to x2, and then we just sleep 1. Okay, so x3 can be wired up to x0, and x2 can't go anywhere where it's at. If I move you up, x3 can go there. I can't move you higher because I need that pin input. Yeah, I can't put you up there because that pin input is problematic. I can't move that piece at all. I can't reverse that around. So I need P0 to come in like that. But I also need to be able to get X2 out. I guess, theoretically, if maybe you're like that, then I can get X3 up there, and I can get X1 communicating like right there, and then here I can have X1 as my input. Right, move X1 to the accumulator, yeah. And so that's outputting on X3, and then that doesn't solve my problem. That doesn't solve my problem at all. If you're up against the wall, I need X2 to come out. Cramming stuff in is the hardest challenge in this game. For real. For real, for real. Where else? I can't put that anywhere else. I could maybe. I can't do that. Trying some layouts in my head. I'm trying to figure out. We've got a lot of code that we're doing. We've got the pulse manager. We've got to send colors down. And we've got to have all these communicating. But we've got all this. We've got these like notches that we have to fit around. Like nothing can go in there. We couldn't move this forward. If we move this forward, then like this can't turn in such a way that this is still readable. So like we have to be at least one away from it. I'm wondering if we stack them differently. Because like they don't really care. They don't really care what order the colors are. Like we're still sending it in the right place. So this could come over here to P0. And this can come straight to P1. Right? But now we don't have an X out. So we could put a bridge in right there. And then we've got an X in. So that could go there. And then we have an X out there. But we don't have receiving in for this one anymore. Could we move you up now? Could we move you up now? That solves that problem. That solves that problem. If maybe we moved it up here, then X2, frustrating. That really needs to come in there, but that can't go across there, so that doesn't work. I wonder if we moved this back up here where we had it, if we pulled X up there, that's not helpful. We'd have to pull it up like that, because we could then pull this pin down here, like that. So that's an option. But we still need this thing to be able to communicate up. So we need an XN. So that's our XN right there. And really that just needs like X3 out. And I guess that needs to go there. Actually, you don't communicate there. You communicate there. Oh, that might actually work. We've got our XN. And we've got our X out. That might work nicely. Yeah. Okay, I think we're onto something. All right. So we have this logic implemented. That reads out to these. We're not outputting on P0. We're outputting on not P1, but we're outputting on P0. Green is our second number. So that's green and blue. Green needs to go out on P0 now. Okay, fix the ordering there. Now we just need to re-implement this. We don't need to re-implement all of it. Right here, we're going to do a read. So when we read, we need to move 1 to X0. We need to move 1 to X0. Because that's going to tell X0 to write the numbers. Then we're going to move, what do we have? You are X1. Move X1 to X0. Move X1 to X0. Move X1 to X0. Move X1 to DAT. That is our count. If we're not reading, then we're doing our count. So for count, what we're going to do is we are going to move Y0 to X0. So we're going to tell it to tick, and we're going to sub 1. Ooh, that's going to sub the accumulator. We're going to put you into DAT, and we're going to read into the accumulator where we need to do math. We're going to test equal accumulator to 0. If it's 0, we're going to 0 things out. Well, we've already told them to do something. So we actually need to do this test first. If we start at 0, so this will be 4. We write 4 here, and that's the first turn that we write that. Then we have 4, so we have 3. Then we sub 1, we're at 2. We sub 1, we're at 1. We sub 1, we're at 0. We still need to output at 0. So only if we start at, well, even if we start at 0, that's 1, 2, 3, 4. Well, that's 4 ticks. So I don't know. Let's just go with it, and we'll see if the logic doesn't shake out. We'll adjust it accordingly. So what we're going to do is we're going to sub 1 from the accumulator. We don't need to pass in. We just sub 1, and we test equal accumulator 0. If it hits 0, we move 2 to x0. Otherwise, we move 0 to x0, and then we jump loop. Okay, so let's see where we're at. We read, so we pull in our one value. We're saying we're going to write data around. That writes a 1. That wrote a negative 999. Okay, this logic is backwards. We're writing 1 there, and we're writing and we're writing 2. Oh. Yeah, sleep. Needs to sleep. And that'll automatically wrap around. We don't really need that label. I don't think that label matters, but we don't need it, so let's get rid of it. Okay, what were we doing? We swapped these around, so x3 now only points to red. So we move red to x3. We move green to x2, and then we move this needs to come up. And yeah, then we move both of those to x2. Okay. I still don't know why we got negative 9999. So it's greater than 9999. That is accumulator. There we go. Okay, that solves that. We sub 1. Yeah, we push 0. That pushes zeros. Why didn't that do anything up here? We got move 0 to x2. Shoot. Yeah, moving's already kind of expensive. We don't have a way to zero it out. So I guess instead of zeroing them out, we just need a way to tell them to push 0. But how do we tell them to push 0 without storing all of the color values? This is what's so annoying about some of these games. Like, this would be easy to solve if we could store data. And we have a way to store data. But it says part not recommended. So, like, yeah, we could implement with that. That would probably hurt our solution because we can put it out there. But that'll probably hurt our solution because we're using a part that's not recommended. So we need to just write these values to the pins until they change or we zero them out. So maybe we're overthinking this a hair. I'm curious if we just wrote, that probably won't run. Let's just connect them. That's fine. We're going to rewrite this anyways. I don't know why I unwired that. We're going to move 100 to P0. We're going to sleep for 2. Then we're going to move 0 to P0. We're going to sleep for 2. Okay, so let's check it out. Boom. We got 100 in P0. That's exactly what I thought. Yeah. We are overthinking this quite a bit. Actually, I don't know if that's what I thought, but I'm pretty sure that's what I thought. So we don't even care about these at all. Because writing to these pins, these color pins, is going to persist that value in a way. Like it doesn't reset the power. Which means we can go back to here where we're moving these, so RX comes in. We do still need an intermediary to give us 3 pins. So we need a pin. We have a pin here. Let's move you up some more. Move you up some more. So we can get a pin here. All right, so we've got 2 pins. So we're going to read. Let's just rewrite this, right? Okay, so move. We may still need more. All right, what I'm thinking, let's talk approaches real quick. So if these store output, we're just going to write to them, and we'll worry about updating later. We're just going to get one step at a time. So let's get this first packet, let's get it working to some extent, working. So we're going to move X1 into DAT. We're going to test if it's greater than -999, because if it's not greater than that, then we have data to read. So that's where we jump to read, and that's where we put read. So read is going to move the DAT value to P1, which is red. It's going to move X1, which is green now, to P0, and we're going to move. We can push that further that way because we are going to need to bridge these together. Or actually we can forego the bridge. I don't know if it's more elegant to forego the bridge, but we can forego the bridge if we put you right there in the middle, just like that. All right, so now we're going to move X1 to X3, and we're going to move X1 to P0. Then we're going to move that final value into the accumulator and jump loop or sleep. And then we have our sleep here, of course. That's our sleep one. Okay. This one will sleep X0, and it will move X0 to P1. That's all it really needs to do. We just need a dummy to push our new value through. So that should read 999, and then we push in colors. We've now reset our colors. Why did they get reset? Is it as I feared, or are we writing 0 out? Yes, we are reading. This needs to jump sleep. Yeah, okay. So here we are, we're reading. We're writing color values. And then we sleep. And now we keep that color value going. So while we're here, if we didn't receive a new packet, we need to test if accumulator is 0. If it is, we need to 0 everything out. So we need to move 0 to P1, move 0 to X3, move 0 to P0. And that is where we encounter an issue. We could put sleeps in here as all like pluses. I guess we don't even need that jump there now. So that saved us a few lines of code. We don't need that one there. If it is 0, then we do that. Otherwise, we sub 1. And then like we sleep. Is that doing it? We've got a color. We're subtracting. Boom. We receive a new packet. We write our new colors out. We 0 everything. And we get another packet. Okay. Okay, this looks promising. We even support interruption. All right, I think we did it. We were way overcomplicated that first round. We were trying to fit everything in. Look at that. Look at that. We are, except for power usage, we're pretty average. I really wonder, out of curiosity. No, because we do need to sleep 1. Whoops. Didn't mean to do that. There are factors we control, factors we can't. We could not control the fact that Cool Dad was arrested and jailed for possession of amphetamines as he attempted to enter Japan, thus canceling the world tour. Well, that's that's one reason to stay away from products like this. Okay, what was I saying? So, yeah. So I don't think the value's none. Ooh, interesting. But I don't think we can read it really. Like we can't really, like there's no value, but we can't sleep until there's data because that doesn't tick. Like something still needs to tick every one. We still need to write zeros. We could put something else that ticks in, but I think that's going to cost more. And another thing to always remember with Zachtronics games, I think I'm going to leave it as is. I'm not going to try anything. I was going to try to potentially address the power issue, but again, one thing about Zachtronics games is that you may not be able to optimize all 3 of these at the same time. Like to get better power usage, you probably need more components. That way each component is using less power or sleeping longer. And to get better production costs, you obviously need fewer components, right? So your components are going to do more work naturally. We're kind of trying to optimize somewhere in the get it to work, move on approach. All right, device 2827 from Outreach. Poseidon 779, a decentralized autonomous corporation, has determined that a thorium mining operation can be optimized by as much as 2.7%. That's a small amount. The specifications are included in this communique. Please create 50 of these devices and ship. What is this? A decentralized autonomous corporation is a company run without human involvement. It has money and investors, but it makes decisions for itself on what to do with that money, using information from multiple lower-level monitoring and analysis programs. Interesting. An autonomous corporation. All right, we've got X, Y, power. X and Y are simple inputs connected to an unknown device, presumably some type of motor or high-power switch. We're going to map the XY coordinate to the corresponding power value as specified in Poseidon 779's geometric specifications, which can be found in the supplemental data section. Okay, so we have an algorithm that we need to implement. It is in the document. I am going to pull it up, and I'm going to do my darndest not to leave it open. So we're gonna try to not leave it open. That's a goal here. We need to go to the supplemental section, and we're looking for something about spoiler related, the assembled meat primer. That's the carbine target, the creepy sound effects page. Poseidon 779 thorium unit, actuator control subsystem. Geometric specifications. Okay, understand this is a geometric visualization of a state space. The 2A27 actuator control must take a value as shown in specifications dependent on inputs as described. Understand the zero value area in the middle is required so that the actuator avoids the flux point, which is here. Create a device that maps given coordinates to the corresponding power value as specified in this geometric visualization. So we've got some constraints here and some power values. Looks like if x is greater than 20, but less than 40, y is pretty simple. Y is pretty simple. So I think if we map this space first, which doesn't care about y, notice there's no y restrictions, then we can map this one. But I guess we do need to consider x. We do need to consider the x value when we test this. There are a few checks here. I think the ones that matter the most are these two, because they're dependent on both of them. So let's start simple. These are pins, so we will need more than one tool. So the first thing we're going to do is let's try and get this one over here. Clean that up a little bit, and that's not what I meant to do. There we go. Let's clean that wiring up. Okay. So that's P0, right? Yeah, that's P0. Okay, so what are we going to do? X is P1, so we're going to move P1 into the accumulator, move P0 into DAT. So Y is our DAT. Trying to think. Yeah, I think I got it. Actually, I think I got it. Yeah. If x is less than 20 or greater than or equal to 60, don't worry, I haven't done a lot of work yet. I haven't closed the specification on purpose. So if x is less than 20, it's 30. If it's greater than or equal to 60, it's 30. Otherwise, it's 0. So we can start assuming that our initial value will be 0, and then we can do the test to set it to 30. Then, if y is in this range, we add 50, because 0 plus 50 is 50, and 30 plus 50 is 80. Well, I guess we do have to verify that x is still in this range too. There's not really a way to do an and, is there? Yeah. Yeah. So I wonder if instead, all right, we're gonna approach this. I think in parts. Might cost a little bit more, but I think it'll be for the best as far as like simple implementations go. So let's dive in. We're gonna like I said, we're gonna do it in parts. So we're gonna have like part 1. Let's just gonna ditch this altogether. We're gonna do part 1 is gonna work on x. Let's read our x in. So x is pretty simple. Let me pull my specification back up just so I can reference it. So if x is less than 20, if x, move P0 into accumulator. If it's TLT accumulator, if it's less than 21, so that's less than 20. So if it's less than 20, then we want to output. We want to output 30 to P1, and we want to also sleep. If x is greater than or equal to 60, so if it's greater than 59, then we will move 30 to P1, jump sleep. Finally, we move 0 to P1, and we have sleep as sleep 1. So that's going to output our x value, and it's not going to do it on x1. It's going to do it on, or not. It's not going to do it on P1. It's going to do it on x1. So that's going to be our x value. That's going to give us 0 or 30. Then we're going to do a little bit more work on y. So we're going to pull in y, which we definitely need. We also need x, because that's going to basically determine. So we're going to move P0 into the accumulator, and we're going to move we're not going to do math on it. Let's put it in DAT. We're going to move x0 into the accumulator. And then we're going to basically like test equal still don't know how to do and. So and would be like a value of 1, but we've got to add two things together. We don't have a 0.5. We could divide by 2, but we don't have a 0.5. What is 1 divided by 2 here? I don't think this is going to work because we're waiting on that. If we sleep 1, that'll probably be fine. And then we can put something else out there to just throw some values in it. So move 2 to the accumulator, divide by 2, right? So that should give us 1. If we we can't step invalid instruction div. What is divide? What is the divide instruction? I thought it was div. Don't we have all math? Da 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 da. We got registers. We've got multiply. We do not have the ability to divide. We're probably going to have to implement division at some point. Well, that stinks. That stinks. So how do we get there? How do we do an and? We need to say if x and y are certain values, we need to manipulate the input. Obviously, it's like a multiplier, right? So we like start with 80. If x is that value, we multiply it by 1. I think that's it. Yeah, that's probably it. We start with the assumption that we're going to add to it. So we'll move 50 into the accumulator. Right? And then we move P0 into dat. That's not going to work because we only have two things to store. We can't pull in y yet. We can't pull in y yet. Or x. Sorry, we're in the y node. We can't pull in x yet. So we need to... I think we can read from a pen multiple times. We could read x. I don't know how hacky that is. We've already got x converted into our 30, 0, or 30. But we do still need to check the x value. Because if x is 40 or 80, yeah, I think we do need to read x in here. Which probably means, it doesn't probably mean, it actually means, so that we need to clean this up some. So x goes to P0, and we'll just have it go to P1. We'll have that go to P1, like so. And we'll connect x1 and x3, like so. Actually, we can bridge that one. Ooh, but then we don't have our output. We do not have our outputter. So we're going to bridge there. I guess we'll bridge there. And then we'll have our output. All right. So you do the x calculation. Then this one's going to move 50 into the accumulator. And then we do the x tests because we need test equal x is greater than or equal to. So I guess greater than P0 to 39, right? If it's greater than or equal to 40. So if it's greater than 39, we mole accumulator, or we mole 1. And we test that it's TLT. P0 is less than 80. We mole 1. Or we mole 0. Mole 0. So if either of those are false, we multiply by 0. And if either of those are 1, we multiply by 1. So we start at 50. If they're both true, that's multiplied by 1, which is 50, multiplied by 1, which is 50. If the first one's false, we multiply by 0, that's 0. Then we simply, we need to add x0 to the accumulator. Move P0 to dat. But we need to decide if we're moving 50 to the accumulator first. So we only do that when y, which is P1. So we're going to test greater than P1 39. We're going to mol 1 or mol 0. And then TLT P1 80. We're going to mol 1. Oh, dang it. Dang it. I don't think that's a dang it. We do need to read X and Y, but we can output that from here. So we don't actually need to read that in here. That could go over here. So we move 0 into the accumulator. Now that we don't have to add that, we still have all of these. Reading them both. Mol 1. Mol 0, right? So we still have the sleep, so we don't have the ability to write it out. Which to me tells me that we do multi-stage on the Y. So the first thing we need to do is we need to get Y processed, right? So like, what is Y? What is Y? We're going to test Y first. So we're going to test Y. Then we're going to output that here. Where we bridge. We bridge that down in there. That's supposed to be P0. Then we move accumulator X1 and we sleep 1. So that determines our Y multiplier, right? Then we do our X testing here, where we are going to basically move X0 into accumulator, and we're going to do the same thing. We are testing if Y is good, and then we move that final output to X1. And X1 actually oh, that does need to go there. So we simply move accumulator to X1. Over here, we simply move X1 into the accumulator, and then we add X0. And then we move the accumulator to P1. Then we can SLX X1. Okay. Oh, but we got a power spike here. What happened? We're getting 18 in, so 18 does not fall within our range. We should be putting a 0 out. And that puts a 0 out. We're good. Now we read a 32 into y. So that outputs a 0. All right, we move 50 into the accumulator. P0, 48 is greater than 39. P0 is less than 80. So we put a 50 out. X is 31. 31 is not greater than 39. Ooh, there's our bug right there. That multiplied by 0 is a plus and not a minus. So that should get us... There we go. Okay. Boom. Probably more components than we should have. Yeah. Yeah, we're high on everything. Lines of code, power usage, production costs. That one's tough. There's probably a better mathematical solution here, but it's tough. Let's just look at like production costs. Like we've got a lot of logic in here. We're doing a lot of tests to add that 50, that like little XY block of the 5080 is really problematic. I guess if we started X at 30, we could say like, if it's greater than 20, subtract 30. If it's greater than 60, add 30. And then Y. See, we can't just do the 50 with the Y values. We have to take into account X, because if X is less than 20, we're 30. But if X is less than 20 and Y is greater than 40, like 41, then that does technically fall within our add 50 range. Y is the smaller one, though. We couldn't just say if Y is in this value, start at 50, because we still need to account for X. If X is less than 20, so if we put 50 in for Y, so we say Y, if Y is in that range, we start at 50, so we put 50 in the accumulator. And then we do our X thing, where we're just going to count through. So if X is greater than 20, or we add 30, right? We add 30 because that's where X starts. If X is greater than 20, which if it was like 19, then we would say it's not. We actually have 80 in our buffer, which is wrong. That's wrong. I guess we could do it from both angles. If X is less than 20, add 30. So we could start at 30 so we can get rid of that test. If X is greater than 40, add 50. But it's not just 50 because it's 0 around it. I don't know. I think this is good. There is undoubtedly, obviously, a better solution, but I'm going to live with this one. It gets us through the problem, and we get to move on. Payment en route. What a future we live in. That was cool. Was that cool? Chatting with a mate at the pub. Microcontrollers we use everywhere have a secret instruction that isn't in any of the documentation. Takes the format of gen PRIRI, and it conveniently generates a pulse on any simple I/O pin. The signal switches on, then off, for however many units you want, using the last two operands. So gen PXY is equivalent to move 100 to P. Sleep X, move 0 to P. Sleep Y. I could have been using this all along and saved so many instructions. It is in the documentation, the Chinese version, just like the at conditional. The what? Seems like many instructions are not translated yet. Putting an at symbol at the beginning of an instruction causes it to execute only once. How have you been initializing code? I haven't really needed to initialize much. To my fellow expats, have you gone to the Three Kingdoms land yet? I just went to the one in Shenzhen, the recreation of ancient Chinese society. There's extremely fascinating. Wouldn't a coin machine be a little out of place at a theme park that's supposed to be historical? The machine will have a beautiful carved faceplate design with dragons and heavenly mountains. Okay, so we're doing a machine thing. We got a price. N1, N5, and N12 are simple inputs connected to a mechanism that accepts and detects 1, 5, and 12 yuan tokens. I assume that's what that symbol is. Bell is a simple output connected to a solenoid that rings a small bell when triggered. Out 1 and out 5 are simple outputs connected to a mechanism that dispenses 1 and 5 tokens as change. After a sufficient number of coins have been inserted, the payment kiosk should ring the bell and dispense change as indicated in the verification tab. So we get 2 12s. Price is 16. So that rings the bell for 1, 2, 3, 4. Is the bell always 1, 2, 3, 4? Yes, the bell is always 4. And then we output 1, 5. So we got 24 in, minus 5 is 19, 18, 17, and then 16 down to the price. Interesting. This is a tough one. Without division, this is going to be tough because we need to output 5s first. So I guess we first gather towards the price. But we don't have anything with 3 pin inputs. I swear, we don't have anything with 3 pin inputs. That's quite frustrating. We could write the money into here. Is that really valuable? Like how much money has been added? Potentially valuable. Coins can't be added at the same time, I don't think. That's probably not a tested case, presumably. This is interesting because all of the inputs are, if this is 100, like I don't think this is going to work. Yeah, that's not going to work. I don't think that's going to be useful for us. Yeah, we could use it to set the bell, but that's a lot to set the bell. We just learned about the gen command, so we can set the bell easily. Okay. Sorry, I was thinking. So, first things first, everything starts at 0. That's perfect, I think. We want to take in coinage. So, coinage input is actually pretty simple. We got 2 outputs they can write in there. Do we want 3 of these? Well, you can receive 2 P's, right? And we're going to do that. So we can move you over there. So you receive 2 pins inputs. We'll bridge that so we can pull our data. So that's our address and our D. And then we simply just need another one for 12. Oh, but then we're going to have to count. We're going to have to count. We are going to have to count. Like we need something reading from that. Yeah, I mean, that's fine. We're going to have something reading from it anyways, because once it's greater than the value, like that same frame, we're going to start dispensing tokens. Well, we can't do that on the same. We're in a bridge. Actually, we don't even need to bridge you now. We can just do that. It would actually kind of be great if we did the same pin layout personally. So x0 is address, x1 is that. All right, so I guess we move 0 to x0. That's the address we're in. I guess we move D0 then to accumulator. Move 0 to x0. We need a reset. It's not D0, it's x1. Move 0 to x0, so we're resetting the pointer. And yeah, I think this is really complicated. We want to add to it. We don't need all of this. We don't need all of this updating the address. We don't need all that updating the address. We do need the multiple pin inputs here. We probably do need this bridge here, so we have our output from there. And then we have this one where we need an X output here. These X outputs can join together like here. And then you because this is just gonna set the cost basically. Ooh, yeah, we're gonna need a big one because we need the X's. We need the inputs and the outputs. Okay, so this is gonna sleep x0. So we get a value on x0. So let's just fix that. So we are going to test equal p0 is 100. We're gonna move 5, 1 to x1. We're gonna test equal p 5. I guess we can just jump sleep. Test equal p01 is 100. Move 5x1, and then we can have sleep at sleep 1. Then we can basically copy this. We just don't need this part. And we are sending 12 over. Then here, we're going to sleep on x0. We're going to move 0 to x3. If we always reset, we can always assume it's there. So we're going to move x2 to accumulator. Move 0 to x3. I guess we'll do that when we write it. Add x0. So we add x0 to the accumulator, and then we're going to write it. So we move 0 to x3, and then we move the accumulator to x2. So that should handle coin inputs just fine. And if we step through there, we send wait a sec. We sent a signal. All right, let's step through here. Boom. Okay, so that one is 100. We send 12 over the wire. Add x0 to the accumulator. Move 0 to x3. Then move the accumulator to x2. Why doesn't that work? Why doesn't that work? Blocked on right. Yes. Why is it blocked on right? Why can I not write into the data? The random access memory. Where are you at, RAM? Okay, here we go. We've got x3 is wired to 0, x2 is wired to D0. So we write to memory, move 0 to x3, right? And then we move 0 to x2. So we write three values, 69, 85, 72. Then we move 2 to x3, which is 0, 1, 2. Which we just started, 0, 1, 2. Yeah, that's the last value we wrote in. And then we move x2 to x1. x2 to x1, which is the output. Yeah. Move x0 to x2, though. Why? Is it because there's no other command here? Like if I put a sleep 1, does that magically make it work? Is this like ROM or something? Oh, maybe that's the problem. Read-only memory, 2000p14. That is the coloration difference is very subtle. But that was read-only memory. That's why it wasn't writing. So that now writes our total in there. Wait, what? Right here. We need to move, yeah. So anytime I do an operation, I should make sure I set the pointer. Like this is what I want to read. I want to read the value at 0. And then we set the pointer to 0. We pull in, we add 24. We set 24. So that's like perfect. And that's also the frame where we need to do our check. We need to do our price check. Price checker. So we need our price checker, which is going to be like our bell ringer. We can only get in here. Can only get in and out on a single. Like we need you like down there. Don't know if that's going to work. Probably not. That's probably not going to work, but that's okay. We could move you down. Like that. We could move you down there. And then we have We have x3 and x2. These don't need to communicate at all. But we do need, I still only have one to get out of there. Can I collapse this somehow even more? Like if I were to do that, could I save anything here? I don't think I can save anything that way. If I bridged these here, then I could move that there. But what is this x1? I can output on x0. And then move that there. Okay, so that condensed that ever so slightly more. Does that help me here? I could get D1 up to X1 and probably put U in for X3. So we could probably get away with moving you back here. A1 could be wired to X2. But I have a lot of pieces left here. I need to dispense coinage. This needs to trigger the bell and dispense coinage, so I need both of these pins. So no, that doesn't solve the issue that I had. If I put this up here, I can get that in. And if I put it there, yikes. What do we have here? What do we have here? So we basically just need some X outputs from these, and they need to read pins. This one can read. This one can read a pin there and there. And then X1 can be connected. Wow, we don't need all that bridging. P0 is now 5 though. And P1 is now 1. These don't really need outputs at all. Like they don't need a pin output there or input. So we move that back there. But did that actually save us any space? Like if I put you here now, and we like put you up there, we still need that pin output. We still need both pin outputs. So we put you there. We've got like D1 that we can route up here. Oop. Up here. We've got price that we can put in there. And then we've got A1 that we can route there. That does leave a pin output for the bell. Does that leave any room for anything else? It does not really leave room for anything else. So we don't have a way to tell it to dispense anything. We don't have a way to dispense anything. Dang it. We could use that to dispense, but we'd have to write. But we'd have to write like a 0 into it on the frame after, which doesn't really trigger. Like let's just do this one, right? So we're gonna We're going to move 0 into x2. Then we're going to move x1 to accumulator. Then we're going to test if the accumulator is equal to the price. Or I guess if it's greater than the price. If it's greater than the price, then we jump bell. And if it's equal to the price, we jump bell. Otherwise, we jump blue, sleep. And you can see that that doesn't leave us any logic to dispense money. We do have a lot of room in here. We could definitely put this logic in here. We couldn't sleep X anymore. But we could always read a value from X. So getting rid of one of these is probably the answer. Jump sleep. So let's put our sleep in there, which is going to be sleep 1. We're going to put our bell in there now. And so when the bell starts, we just gen 4, because it runs for 4, right? What was gen? Let's go back. Let's go back and see what gen was. Gen was gen pxy. Sleep X, then move 0, sleep Y. That's a pulse. Yeah, that's a pulse. It generates a pulse back and forth. So we can't use that. Yeah, we cannot use that. But we can't use it because we don't have a down sleep. I mean, we could technically sleep for 999 Gen 4, but that kind of just runs. We need something that writes 100, sleeps for 4 seconds, and then kind of dies. That's kind of where you come in. Right there, my friend. Which sucks even more. We don't have room for it, really, but we're going to sleep X0. And when we get a value, we're going to move X0 to accumulator, then we're going to move 100 to P1. We're going to sleep for 4. We're going to move 100, 0 to P1. And then we're going to sleep on X0 again. So that'll ring the bell. Yeah, and the reason is the pulse will generate like a pulse, right? Actually, let's go back, because I think early on, what just happened? There was an extra control panel datasheet concept spec. This is like a Steam Workshop. These are custom specs. Okay, so we've unlocked that. Sorry, what were we doing? We're going back to like early on, I guess. So security camera fake. This one generates 2, right? Active and network. So 1, 2, 3, 4, 5, 6 off. 1, 2, 3, 4, 5, 6 on. So 6 on, 6 off. So actually, if we sleep for 6, then we gen. We can't gen. Like, we could gen. Let's just do it. Because it's gonna be wrong. But we've already solved this one, so it doesn't really matter. We want to gen P0. We want to do it for 6 and 6, right? So that immediately puts us out, like that puts us on the opposite, right? So then we would want to invert that. But I don't think we can specify like the accumulator, right? That's going to be invalid. Yeah, so that's invalid because it must be a simple IO pin. So yeah, so we need a predictable downtime in order for gen to be usable. And we don't have a predictable downtime. We have the opposite of, oh wow. How did it go? Boom. Being first is great because you get all the nerves out of the way. Sorry I'm a little late. I've been stuck on this problem deep in my head. But that is very exciting. Yeah, so we can't gen. We do have to move like 1x0. Now we need to dispense coinage, though. And the dispensement of coinage is difficult because we have a value. We need to tell something to begin the dispensement of coinage. At the same time, we basically ring the bell. We say, ring the bell, dispense of the coinage. Okay, so let's start eliminating some of this stuff if we have any redundancy here. So this one could be part of here. So this sleeps X. So basically, instead of sleeping X, we will we'll do this. We'll move the values into it. We'll add X0. And then we will do P0, 100, add 12. That needs to be plus add 12. And then we copy it on. Yeah. So then you can go away. And we can bring you back here. And then maybe put, ooh, that doesn't work. Let's bring maybe you up. If I bring you up, I have to bring you out. Which means that doesn't work. Because that has to go there. Which means you need to come out 2 spaces. So I can get that in X. Okay. So then we move 0 to X3. That did add some room, though. We did add some room. Move 0 to X3. Move 0 to X2 to accumulator. I'm the example for all. Oh, goodness gracious. I feel bad for the rest of them. Yeah, you set the bar like way up here when you start, and then it's can only be downhill from there. All right, so we move X2 into the accumulator. We add X0. And then we check 12. We add 12 if that's true. Then we write that back and we sleep. So now instead of, I mean, we can just remove this. It was saving some cycles. But you know what? Who needs it anymore? Who needs it anymore? Actually, we do need this. We do still need that. Oops, we do still need that because we need to jump sleep here, and then finally we will move 0 to X1. So we have to write something to X1 every power cycle. Okay, now we can start trying to rewire some of this other stuff up. So we have the bell. We can replace the bell with this thing. Do we? No, we don't want to replace the bell with that thing. No, we don't want to replace. I mean, we do want that thing. We do want this. I don't know what I'm saying. We want this. We want that because we need to output there, and we need to output there, and we need to pin that somehow because we need data. And we're back at the size issue again. Oh, mother of pearl. If both of these were up here, I think I can move this out. Move this out to there. Move this somewhere. Put it somewhere. Thank you. Okay. I just need them out of my way so I can think. If these were maybe in sequence down here, or up here actually. If these were in sequence up here, that could go there. That, I don't want to merge those. That could go there. Okay, so that gives room up there. That lets us put this like back here, I suppose. We can put this back here because we need that. And then we need address, and we need that. This also needs adding and subtracting, I don't know. They don't happen at the same time. So we'll just assume that they will never happen at the same time. The address is X3, so X3 needs to be wired to our address, which leaves X2 wired there. I know that we could put in a bridge there. So we can probably eliminate that. We could put in a bridge there, but it doesn't really provide us value. Okay, so for the bell, we don't have a way to signal the bell now. Shoot. A lot of fat good that did us. We actually hit our little dude. We don't need you back there. We actually hit our little dude pretty deep in there. Pretty deep in here. We hit our little dude. So I think the challenge of this game is like the logic is pretty easy to write as far as like solving the problem. Like we basically have everything but the dispensement code. But it's making everything fit. That is proving to be the biggest, most troublesome puzzle piece in here. Yeah, so that's frustrating. That's very frustrating right there. We could move these bridges up a little bit. I don't know why I would bridge that. I can just go right there. Yeah. Don't know that a bridge is helpful there. We only have a P1 out from there, which we can't use. We could use a P1. So like if we did bridge that, we've got a P1 to P0. Okay, X0 is not connected. It's X1. Oh no, that doesn't need to go to X1. That needs to go. If accumulator, yeah, X1, move P1 to P0. Is that? Did I just? No, I didn't. I didn't do anything useful at all. Because I need this one. I need these to tie up. Like I need you to link here. So that's unhelpful to link that way. And then I would need that to link in there. So this bridge is great, but then it cuts off my ability to bridge here, which I need. And then I lose my pin, so I can't write to the outputs. Okay, let's wipe it. Let's wipe it. Just delete it, and we're gonna start over. I don't think the code is hard. It's positioning everything, and I have a lot of cruft in that last one that I don't want to have to deal with carrying over. So we're gonna make sure that we keep it this way. My mic output is suddenly really low, so we're going to crank that up a little bit just to make sure, noticing it a little late. So this time, let's start with a big one. Let's start with a big one. We're going to read P0 in. And we're going to read... Let's just move it that way. We're going to read in those values. I need both of these out. I need to go over both of them. So I guess we need to pull you down. Need to pull you down so we can go over the top. Okay, then we need this one. We need a pin input, and we need to reach up there. Basically, we're going to do exactly what we had done before. So we need our random access memory, not read access memory, where our address is on top. Yep, so we're going to move 0 to x3, and then we're going to move x2 to the accumulator. So we're going to pull that monetary value out of the accumulator. Then we're going to do our adding. So we're going to test equal P1 100. Then we're going to add 1. Test equal P0 100. We're going to add 5. Then we're going to add x1. Then we're going to move 0 to x3. And we're going to move the accumulator to x2. Then in here, then I guess we'll sleep 1. Then in here, we will test equal P0 100. We will move, if it's 100, we will move 12 over x0, or we will move 0 over x0, and we will sleep 1. Okay. So we've now wired those two things up. We now need to dispense money. We can't get P out, so that's not good. I think the determination of the data, we could use the X one, right? So we've got X's here. Like we just tie that in directly. Oh, we don't want to tie that in directly because we need to update the money. We need to update the money. So, yeah. Snap. Could you at all go here? The answer is no. You couldn't even go there either. You could not even go there. You really can only go like basically here. Could you go out some more? Could we deal with you there? And then that's not valuable. Right, bridging that down. But then I could bridge that down. And I could put the X guy here. Like that. And then we could put the money here. But do I have enough logic in here? So what we're going to do is we're going to move 0 to x0. And we're going to move x1 to the accumulator. We're going to test if the accumulator is equal to price, which is x2. And we're going to move 1 over x3. Actually, it doesn't really matter what we move over x3. Test greater than accumulator x2, move 0 x3. And if neither of those are the case, then we will simply sleep 1 and check again next frame. Oh, that's not too bad. But our dispensement logic, we need access to both pins. We need to get both pins out of there, like the bell. The bell dispensement only needs to trigger when that hits 1, but we can't wait for it to hit 1. We need to know immediately. So it's like it needs to write to it being 1. But then this needs to basically subtract these values until they are correct. We could put you like that. That gets us that, but it doesn't get us data. We can't read data. So we would need something to tell it how to pay. If we move that out 1 more, that doesn't solve anything. So yeah, so that is a failed implementation, a failed layout. If we move that back, where else could you go? You could go there, but then we can't signal the bell. We can't signal the bell. We would have to do that for exactly four units, which we just don't have the ability to easily control here. We could put 2. We can't put 2 of you because we don't have read write. So I need read write lines out of here. But I need read write from this into that. If we put this on the bottom, we're getting close to back to where we started from. We'll have to change the value of these numbers. But potentially we are okay. I don't think that takes up less room. Maybe it does. It doesn't create this divide. It gives us more space in this region. We do need to adjust numbers. This one is now tied to a value of 1, and we're writing out on x1. This one is, the P1 is now tied to a value of 5, and this one's about 12, and then we are adding x0. 3 and 2 are the same. X3 and 2 are the same. We're still writing the summing. So we've got that part. That part, for the most part, that part works just fine. What we don't have is validation of these values here. And this part is not on the board. X3 needs to write out to something. But then we need to edit these values, which means that we need them to come out. Like, we need to get them out of here. Which means, like, maybe it needs to be... So frustrating to place this stuff. Okay, so if you were here, it's not helpful. Yeah, that's not helpful. I don't like these nodes. I don't like any of these nodes. This is why am I struggling so much on this problem. The implementation, again, is pretty simple. Trying to get all the parts laid out so that they work. Like, we can get pieces of it done, right? Like, this works. We can check this, and we output this. This signals to start spending money. So I guess, actually... what we need to do is we just need to send that money total. I've been like trying to blindly send a signal. But what we really need to do is just send the money total. Right? And we can link that up there. Ideally we bridge it so we have some space. Well, we need 2 wires to come through here, which we can't fit through there like that. But if we don't need to branch off there, we can just tighten that up quite a bit. Okay, so the bell implementation. We can trigger the bell implementation up here, which gives us basically pass for that. That's what we want. Now we need to get... but we need to get this signal out of here. We need to get this signal up here. I think I need to reorient these again. Now that we have a plan of attack, I think we can get these moved. So if we put you up here, you here. Well, we have a better plan of attack than we've had. Let's go ahead and push you off the board for now. And then we'll put you like X3 maybe. That's tough. That's a toughie there. Oh no, I need pens. I need pens. We do have to come down. That prevents us from getting a pin out. Of course it does. Of course it prevents us from getting a pin out. I mean, we can't even get you in there, and then we get a pin out to like there. And we could maybe squat the data in somewhere. And I haven't even placed the other one yet. Right, that's needed because we have 2 pins here. And then we've got this one who needs a pin and a bridge to get up to X0. That's probably the most compact that's been. That defeats this one here. So move X1. Actually, it's 0, 1, 2, 3. Okay, 0, 1, 2, 3. So X3, X3. Then we're going to move 0 to X2, which is here. Pin is not connected. X1. We're going to do X0 again. X0 again. I wonder, actually, can this be written to? I don't know why I didn't start here. But if it can be written to, then that kind of solves input almost instantly. Like, does that work? I think it's safe to clear. I don't really have a lot of logic that can't be replicated. Can I, like, delete the... No, I can't easily delete the component. Okay, so, like, if I step... So, it's receiving a value, but we're not visualizing it, so let's visualize it. Copy X0 to accumulator, sleep 1, move. One. That should be 5. Okay. Okay, we're on to something. We're on to something. So this can work. This can work. We can funnel input into a single value. But we still need to process that input with a little bit of work. So yeah, we're gonna do that. We're gonna put you there, and we're gonna put our memory here. I don't even think we need that, really. That's just causing more problems than it's worth. So, well, is it though? Is it though? What is 10 times 10 times 5 is 50. We can't do 12 times 100. I want to say that that's... I just need to figure it out. Copy 0, move 0 into accumulator. Sleep 1, right? So we boom. So that should be 12. Not 0. X0. So 12 comes through as, 100. 100 times 12 doesn't work. But we can do simple values. So we move x0 to dat. And our accumulator is our money. Then we can test equal dat 100, add 12. Test equal dat 10, add 5. Test equal dat 1, add 1. With a plus, we need a plus there. Oh, I lost my chat. We need a plus there. Oh, it's 8:20. Shoot. We need to wrap this up. I'm on a roll though. Let's see if we can. Let's see where we can take this. So that should get our money. All right. So we have our money input. We go here. We add 12. We add 24. That's our money. We could tie this in here. So once we've totaled up, so if x3, if accumulator is equal to x3, then we move 0, or let's just jump pay. Test greater than accumulator x3 jump pay. If we do pay, what do we got? We can move accumulator on x2, move 0 into accumulator. I like that. I like that. Okay, I like that because that can signal a couple of things. For one, we can signal the bell. Right? So we're going to sleep on x0. We're not going to read from x0. We don't actually care what the value of x0 is. But we are going to then move 100 to p1. We're going to sleep for 4, move 0 to p1. And then we'll go back. So we've got the bell taken care of. The bell will now work once we hit... move on. Let's pull you down here. So we'll sleep x0 and we'll move x0 into the accumulator. Yeah, let's just do that. Okay, so that gets us. Why is bell sleep on x0? Oh, we need one more line of code. Crap. Okay. Not a problem. Not a problem. We have our little Xer guy here. And it can come here. And we can basically just like put that there. And we can basically copy yeah. Yeah, actually. Yeah, that's pretty simple. We read input. We want to do this here. Let's probably make you a bigger one. Just because you're going to have some code in you. You're not doing the payout, but we are testing x1, x1, jump pay. That needs a positive jump pay. Otherwise, we're going to jump sleep, and we're going to have sleep as sleep 1. Okay, so we've already got a lot of logic there. We don't need pay here. We don't need x3. And then this is going to be move 1 x2. Move 5 x2. Move 12 x2. Does that actually fit? Does that fit in there? Ooh, that does fit in there. Perfect. So that'll save us some x0 to ACC. X1. So x2 goes to x1. Yeah, pretty simple. Shoot. I can't, can I, ooh, I can't undo. Yeah, so what I noticed is we need sleeps in here because we've got to move 0 to x2. If none of those match, then we can sleep. So we do actually need more code, which is fine. Not ideal, but it's fine. Okay, so the first thing we're going to do is we're going to add x0 each round. So whatever the coinage was, we're going to add that. Then we test our accumulator, and we jump to pay. Pay can now do a little bit more. So x3. So we'll output it on x3. So we're going to move the accumulator on x3. We're going to move 0 into the accumulator, because we're basically ditching the money we have left. So this can now, basically, we're going to go right into x1. That way we can bridge up to pin 5, and then P1 can go to out here. So this is our payout. So we're going to sleep x1. We're going to move x1 to accumulator. Yeah, because we have to do math on it. And then we're going to begin the payout. So payout's going to start we're going to sub 5, test less than 0, accumulator. Accumulator is less than 0. So if accumulator is less than 0, then we have to add 5. Otherwise, we move 100 to P0. And we jump sleep. Now this sleep is going to sleep 1, jump payout. Otherwise, I guess that's what we should do. Start. So the first thing we do is we test equal ACC 0, jump, start. Sub 5. If we can't sub 5, we add 5. We move 100 to P1. Yeah. Basically, if we can't subtract 5, then we add 1. Oh, and we need to sub 1 too. sub 1. I've got one more command and I think I need it. Why do I think I need it? Let's just see where we're at. So we get 12, we get 24. We fired that up. We paid out. Oh. Actually, when we pay, we need to sub X1. Sub the price from it. And then we move the accumulator. So yeah, we get to this point. We've got 3. I actually need 2. Yeah, I actually need 2. Dang. I actually need 2. Because I need to reset. I need to reset that. I mean, I need to move 0 to P1 and P0. I could move this here. Doesn't save any lines of code. Actually, it does, because now I can get rid of that. So then we can move 0 to P1, move 0 to P0. All right, so now we come in here. We trigger that. We write 8 over. We sub 5. We say we're just paying out 5. That jumps to the payout. We sub 5. We can't sub 5, so we sub 1. We pay out 1. Actually, these need, because we have this gap here that we're not filling in. We're trying to like jump directly to it, but we want to pay this out. We want to sleep 1, then we want to move 0 to P0, move 0 to P1, and then we want to sleep 1 more. Don't really necessarily like that approach, but let's see how it goes. So we do that. All right, we've reset it. We write 1. We reset it. We do 1. We do 1 more. And then we're good. Oh my God, did we do it? Oh, we did it. Oh man. That one was so no. What the heck? What's going on here? What's going on here? Shoot. The price is 14. Why are we at -7? Test run 5 of 80. We can't reset. Can we simulate 1, 2, 3, 4? You started going too fast. 1, 2, 3. All right. Yep. And then we're jumping straight to 5. Okay, so do I just need to hit advance a bunch of times? Like, is there a way for me to verify a specific test run? There is not. So once we get to 4, 3, 4, pause it. Oh, here we go. Okay, what do we got? We got 1 in, then 12 in, then we got 1 in. Uh-huh. We need like a 0 test here. Like this one right here. Like if we put that in there, let's call it test. If we do that, then on positive, it is 0. We jump start. And then here, we don't have a line of code. We can add 4 because we've already subtracted. And this jumps test. Okay. Theoretically, that should have fixed step 5. It did. Oh, we are high. I don't care. We are high. We did it. We finished that problem. All right. That's where we'll wrap it up today. That was a long one. Both of those problems got really, really complicated, and I'm pretty sure it's just going to keep going. So we'll have to get better at the layout stuff. That's tough. But that'll be the end of it. I hope everybody enjoyed it. Have a good rest of your Tuesday, and I'll see you on Thursday.